Login accepted.
All right. Hopefully everyone can hear me. Welcome to my session about Project Loom. My name is Martin Stefanko, and today I want to talk a little bit about the problems that Project Loom brings to Java, because it's not usually presented. So a little bit about myself. I work at Red Hat, mainly on Quarkus. Can I get a quick show of hands? How many of you are using Quarkus? More people than I would expect. That's great. And Spring Boot? Yeah. We'll talk about it. OK. If you are from Krakow, I actually lead the Java user group in Brno in Czech Republic, which is only 3.5-hour drive. So if you are around, please come. I'm actually currently writing my first book called Quarkus in Action. Really interesting also to Spring Boot developer. So if you want to check that out, there will be links in the end. And you can find me everywhere online as Stefanko on every social media. So today we are going to talk about Project Loom. So who thinks that Project Loom is actually how we are going to write all Java programs? Yeah, that's always only a few people. OK, that's a fair point, because this is what we are here to talk about. I want to start this talk to explain generally how we approach threads in JDK since the beginning of Java. So basically, before Project Loom, or since the beginning of Java, we only had normal threads, like one thread class, which was directly mapped into operating system platform thread. Operating system platform thread is something which is maintained by the operating system, so it's not something that JDK controls. It's typically a little bit more expensive to create, a little bit more expensive to just keep track of, because it requires some memory, even if you are not doing anything inside the thread. So basically, this was the only way how we could basically write Java programs if we want to do something on the thread. I will be using an example where I am creating an HTTP server. So this code is in basically Jakarta EE and microprofile. But if you are coming from Spring, you will probably understand it. So when somebody tries to reach out my get method called call, basically I will make a remote request to example client, which is http://example.com. And when I will do this call, because I basically have only one thread, maybe I should start it a little bit differently. So when somebody calls my get method, my framework, in my case Quarkus, will allocate single platform thread, which will execute the whole duration of the call. So basically, I will get my thread, whatever, thread A, and it will start executing example client, remote HTTP call. Until I will get back response back from that HTTP call, my thread A is actually blocked. I cannot do anything in the meantime. So that thread is basically just wasting resources and waiting for that HTTP call to return. When it returns, I can continue my execution on the same thread. Of course, this brings many benefits, but it also has its drawbacks. So just to put this into the image, we have our request coming to our server. We will allocate a platform thread just for this one request, and we will start executing our HTTP call, whatever. When we will get to the point that we are actually needing to block, we will basically make our HTTP call, and for the duration of that call, we are not doing anything with that particular thread. When we get back response from that HTTP call, we basically can continue normally on that thread. If we have any other requests coming in between, while we are still executing something on that first thread, the only thing that we can do is actually add new thread, which will be handling second request. And exactly the same thing. When it's finished, it's basically that thread is reusable for other threads. So if I have a request coming after these two threads are finished, I can execute them again on the same platform threads, just I cannot mix them. So you see that the problem that we have there is that we basically in that point where we are actually waiting for that HTTP call to return, and that can be any I/O, so when you are saving something to a database, to file, etc. Basically, that thread is just waiting and not doing anything. So before Project Loom, we came up with the idea of reactive programming. What reactive programming did, it kind of gave us headache because we needed to rewrite our codes to use continuations. Continuations are basically just a way how we can specify basically the code that should execute when you will get back a result from some blocking operation, which is executed asynchronously. So in my reactive example, this uni is actually, if you are coming from Spring Mono, so I have a single result or exception. And basically, when I now execute my example client reactive get, I am not blocking that thread which was allocated for my HTTP request on my get method. So that map operation is actually a continuation, which is just saved somewhere by the framework. And when I will get back the response from the HTTP call, framework will find that this is the continuation for that particular call, and it will execute it on the result. That's like all the magic that is in the background. Of course, this is a little bit more problematic to write, a little bit more problematic to debug, and I can understand that. Typically, when you are chaining several of these calls, there is something which we call callback hell. But it solves this problem, because basically, we still are only in a time when we have platform threads. So now, our platform threads are actually called event loops. This is concept coming from different programming language, but basically, the whole idea was that when I get my request, I will just find one platform thread that can execute it. I will start executing my request, and when I will get to the point where I need to block, I will basically just save the continuation, and I will not do anything anymore on that particular thread. If I have any other requests coming in the background, they can actually reuse that same event loop thread. This is the general idea that you are having a queue of requests, which you are basically just mapping to individual event loop threads, because typically you don't need to have only one event loop, but you have way less event loops that you have normal platform threads. So similarly with request 2, when you will get to the point where you need to block, you will just register the continuation and continue. If you then get the response from the first HTTP call back, then you basically can again find just 3 event loop, and it doesn't need to be the same event loop, but in my case I have only one, and you will just continue executing it. Similarly, for my second request, I can, again, if my event loop is already free, I can just reuse it. And of course, if you have a request which is not interleaved with any other requests, then of course that event loop doesn't really need to do any, like always something. So in this sense, you can already see that we are way better in utilizing that actual one thread, because any time that we have something to actually execute, we are executing it on one thread. And of course, you will continue this forever. So in reactive programming, there is one single golden rule: never ever block this event loop thread, because if you will, this whole model is basically going downhill. This is not something that we can control, because you are defining the code which is going to execute on your event loop threads or like any threads. So actually, in Quarkus at least, we are able to detect that you are holding that particular event loop thread for, by default, more than 2 seconds. And at least we will throw at you an exception that you shouldn't be doing this, because if you want to do any blocking operation in Quarkus, you can actually mount it to real platform thread on the side, which is not actually that event loop. So in Quarkus, you have actually a choice on which thread you want to run. So, and this brings us to virtual threads. JDK team understood that the complexity of reactive programming is something which is basically a blocker for many developers. So they came up with the idea of how to basically mitigate this in a way. And basically, they allowed us, or they added a new type of thread, which is purely inside your JDK process, in your user space, and it's not directly mapped to a real platform thread. Basically, the whole idea is that it's very lightweight, so it's very easy to, or very cheap to create. It doesn't take much memory. It's easy to destroy, which is also important. So you at least they aim you to use virtual threads in fire and forget manner. So, because of course, when we used to have only platform threads, it didn't really make sense to just remove them every time and create them from scratch. So we actually pulled them a lot, and we reused them as much as possible. So with virtual threads, we are changing this kind of mentality. And of course, since they are basically only in the user space, there is there is a hardware limitation typically, but you will get to it way, it's harder to get to that limitation. So you can create billions of virtual threads on normal machines nowadays. In Quarkus, we basically realized that there are many issues that basically JDK doesn't really solve or doesn't want to really propagate that much. So in Quarkus, we are a little bit hesitant on diving full on virtual threads. So in Quarkus, you need to annotate every method or class with this run on virtual thread annotation, at least for now. But we'll see where we will get in a few years. So the general idea of virtual thread that from your perspective as a developer, you are still writing the same blocking code as you used to for 20 years before virtual threads. So from your perspective, if not that annotation, the code looks exactly the same. The magic now happens inside the JDK itself. So when I will get my request to my application, now I will again find a new or create a new thread, but this time only this virtual thread. And basically in the background, JDK will actually create a real platform thread which is going to execute my virtual thread. These real OS platform threads are called carrier threads, and they are managed by JDK itself. So when I will get my request, in my Java program, I will create a new virtual thread, which is typically something way smaller, and I will start executing my request. What this actually will do is that JDK will find free carrier thread, and it will mount that virtual thread execution to a particular carrier thread. Of course, when you will get to the blocking operation, now JDK is responsible to detect this case, and it should actually unmount the execution of your virtual thread from the real platform thread. And you are blocking, but you are blocking only that lightweight virtual thread. And you can see that carrier thread is again free to execute something else. So if I have another request, again, fire and forget mentality, I will create a new virtual thread every time because it's so cheap. And I will start, or I will indicate that I want to execute my request on the virtual thread too. And I will find, again, a free virtual thread that can execute it. In my case, again, I have only one, but you can also imagine that there is no any guarantee that one particular carrier thread will be handling the execution of the full request of the virtual thread. So again, when I will get to the point where I need to block, I will just unmount it. When I will get back, where is it? When I will get back a response for my first request, I basically, again, have something as a continuation, but this continuation is now hidden inside your normal blocking code. Just JDK knows that it needs to continue at this point of your method, in my case. And it will basically indicate that this virtual thread one is now ready to continue, and it will, again, find free carrier thread that can execute it. Again, it doesn't need to be the same carrier thread. And you are continuing like, oh, yeah. One important thing that I forgot to mention, when you are done with execution of your virtual thread, it is directly going to the garbage collector. So you don't have actually, well, you can implement it yourself, but typically you don't really keep track of virtual threads. They are really more in the mentality, that basically they are so cheap that you should rather create new virtual thread, not reuse it. So you will continue like this until basically you delete all the virtual threads or you run out of requests. Again, the same case when you don't have anything else executed, there is no need to execute always something on a carrier thread. So if I don't have anything, I will just continue in the similar way. Well, I want to point out that if you put this basically side to side and split it in time, you can see that actually this top side looks really closely to your traditional blocking processing execution, and this bottom part looks dangerously close to the reactive programming and that event loop execution. So as you can see, it's basically the same thing. The basically only difference from reactive programming is that JDK is now trying to hide the complexity of reactive programming from you inside the JDK itself. And of course, this comes with particular issues on its own. So why we are basically a little bit more hesitant on Quarkus side? Because probably you know, if you are Spring developers, that you have since, like I think Project Loom went final, a global flag that will move everything on virtual threads. In Quarkus, you don't have something like this, because there is basically this problem that nothing in life is free. And if you are hiding complexity, that's basically usually the job of the framework which you are using. And that framework is typically doing a lot of stuff on the side, also interacting with JDK to save you from basically shooting yourself into your own foot, which we cannot do right now with Project Loom. So I would split basically the problems into three main areas: carrier thread scaling, thread locals, and basically concurrent access. And we will go over all of these basically in a minute. But before that, probably I can show you, because we have nice time today, so I can show you basically this example in action. So I have my application. I will run it in dev mode. This is a Quarkus application. Dev mode is continuous reload of my application. And I have the exactly same code as I was showing you in the slides, basically here, just augmented with some concurrency tracking, for which I'm misusing messaging. So I have my blocking example, I have my reactive example somewhere here, reactive get, and I also have my virtual thread resource with this run on virtual thread annotation. So in the dev mode, if I press W, and not R, what I probably did. Where is it? Here is it. So this is my application. So here I can basically choose, and sorry for the UI, but I am a backend engineer. This is the best I can do. I can call my application. So if I will try to generate 1,000 requests to that blocking resource, you will see that I will get only to a maximum of 200 concurrency. Why is that? Is basically in Quarkus, and you can see here how it's executing. In Quarkus, you will, out of the box, basically get a limitation to 200 platform threads. But of course, that is overridable, so I can easily change this to 500. And because I have that live reload mode, I can just refresh this page, and it's already reloaded my Quarkus application, so I can apply this right away. Oops, not this button, this button. So you are seeing that I'm getting now to 1,000 concurrent requests. But of course, that also means that I just created 1,000 threads, real platform threads on my machine. And I have a pretty powerful machine, but typically around 8,000 to 9,000 threads, it will not be so powerful anymore. So for the demonstration purposes, I will also do, but I guess you can imagine that reactive will do exactly the same thing. I will reset this. I will also get to 1,000 concurrent requests. But this time, you see that we are executing on event loop threads coming from Vertex project, which is in a core of Quarkus. And if I scroll this long enough, you should see that I only have 2 event loop threads, which are real platform threads, which are now handling that 1,000 requests. So that's quite good scaling. Where then I was. If I try this, let's reset this again with virtual. Of course, my UI is stuck. It happens. But it will show basically what I want to show. You will see that now I'm running on virtual thread. But you will also see that I am running on like 4,000 virtual threads, which is unfortunate because I am kind of misusing virtual threads to actually generate that request. So I can actually also show you the second way how you can utilize virtual threads in Quarkus with this virtual threads annotation, which will inject for you an executor service, which will produce virtual threads, basically new virtual thread per task. One benefit that it will add you, and I will show you later in more basic demos, it will name your virtual threads. So you see here Quarkus virtual thread something, which is very useful when you are debugging. OK. Before we go to the scaling, I want to restart this. So we will start with the, OK, that's slow. We will start with the new state of the application. What I want to do here is now actually grab through, and I forgot to show you this in the output, but that carrier threads are actually managed by fork join pool inside the JDK, which is called like this. So I can actually count how many of the carrier threads I have in my application, which is none right now. But if I generate, where is it? That 1,000 requests to my application, we should see some, because my application should start executing. So I just want to show you that I created just 46 threads just because I was doing the application, and now I want to explain you why. So, carrier thread scaling. Basically, if the JDK cannot really fulfill your need for virtual thread execution in some particular way, it can actually add new threads, new real platform threads to that carrier thread pool, to that fork join pool. So you don't really have any way how to control this. This is done automatically in the background. Well, you have some like hooks, but it's done in the background. So it's just something that you need to be aware of, that usually under traffic, you will get new threads created still, just in way less threads than you used to with normal processing. And yes, just to mention, these are real platform old threads. So this is, again, not something which is so cheap, and it's usually taking some memory. There are 3 properties which you can set to actually manipulate this thread pool which is created in the background for you. Parallelism is basically the starting size, which by default defaults to number of your processors, which is 16 in my case. Max pool size is to maximum number to which you can grow, which is hard-coded to 256. And minimal runnable is always half of parallelism. So it's something that you can tweak, but we will play with it in my demos. So in which cases can JDK actually create new threads? Which are the cases where it basically tells you that I'm not able to keep up with your request? The first problem is called pinning. Pinning is basically a state where your virtual thread, for some reason, cannot be unmounted from the carrier thread. So your carrier thread is also blocked. And you remember what I told you about how this is exactly the same as we are doing with reactive. And as I told you that never ever block event loop, this is also the same for carrier thread. So if you are doing this, this is not so good, because that whole model is basically stuck. And if you basically, because typically this is not done like for one virtual thread, because typically you have something which is executing the same code, like several times. So if you block or pin all your carrier threads, the only thing that the JDK can do is actually to create new carrier thread, and you will again pin it. So you are just in a cycle. So pinning can actually happen in 2 cases. The first one is when your thread holds a monitor, so some synchronized blocks or any other form of monitors. Actually, this should be going away in JDK 23, because this is just internal limitation of how synchronized, for instance, is implemented inside the JDK. I still am yet to try, because there is already first build of JDK 23, so we'll see if my demos needs to a little rewriting. But so far in JDK 22, this is still an issue. And the second one is if you have anywhere in your call stack a native call. And probably this is not something that you can actually control, because we counted inside the core Quarkus libraries, you have 13 native libraries. So if it happens that you are calling something which happens to have a native call somewhere in a stack, and you know like how big stacks are in enterprise applications, then no luck. And this one is not currently, as far as I know, there is no solution for that. Just don't use native libraries. You have actually also a property which can basically detect this state, because this is actually an event that is happening inside JDK. So you can actually listen for it, and it will produce events that you can listen to. And basically, if you add this property, it will print the stack trace, or just the name of the method which is pinning. And probably with that, we can start coding something, because I prefer to code. So I also prepared plain old Java, or plain new Java main method that I want to show you how to work with virtual threads, because it's easier to demonstrate on like very easy code. So I have only a log method and a sleep method just to save some printing. There are basically two ways how you can start with or create virtual threads in Java now. So you have these off-virtual and off-platform static methods on thread class, which will create either virtual or platform thread. So if I want virtual, I can just call it like this, and let's do just start. And here you will just pass the runnable that should do something. So let's do log thread A start, no, sleep for 100 milliseconds, and log not thread B, thread A, end. And if I pull this into T1, I can just do T1 join. And if I now, hopefully like this, Java minus enable with JDK22, so I am not like doing anything which is not top latest, at least so far, you can see that I got my virtual thread code 28, which is running on this worker thread from the fork join pool 1. So actually, my method is waiting for 100 milliseconds, but actually after, basically when I will get to that sleep operation, this is an IO operation, it will get unmounted from that worker thread 1, and it will, after 100 milliseconds, it will be again mounted to the same thread. And if I will be doing this long enough, I will probably not see it, but sometimes it happens if I have very busy computer. But what I can do is just to copy paste this, oh no, into thread 2 and call it thread B and do this. And if I now call this, we should see more worker threads that have been created. Sometimes, because sometimes it's not really this is a good example. So you can see here already that I started thread A on worker 1, thread B on worker 2, and I ended thread A on worker 2 and thread B on worker 1. So you see already that you don't have any guarantees on which particular career thread you are running. And of course, this will be always different depending on how you are running. So now I'm running thread A end on worker thread 4. So this is one option how to write virtual threads. But I don't suppose that many people are really nowadays creating virtual threads manually. Let's copy this whole. I want to share the code with you, whatever I will type here today, so you will have it available. The second option, which is more better in general, is to create basically executors. What? Did I copy? Okay, thank you. Executors, new virtual thread per task executor. And basically, I can just rewrite this now to executor service, submit, and this will give me back future. So I will do the same here. Executor service, submit, and submit will be F2, and replace this with F1 get and F2 get. So I should now have exactly the same thing, just I'm doing it with executor service. What I want to show you here is that actually the naming of the virtual threads is not so hard, because you can very easily just create Devoxx PL. Oops, come on. We will start at 0 and call this factory method, which will give you a thread factory, and all you need to do just to rewrite this to new thread per task executor, to which I can pass factory, and now I have named virtual threads. So it's not so much magic, just you have it automated in Quarkus. Okay, so these are the ways how you can work with virtual threads. Now what I can do is actually show you, and I think I have it here, those 3 properties that I was talking about. So I will actually limit my fork join pool for career threads to only 1 real platform thread. So you can probably expect what will happen. Basically, not much. because I am still like running on one single carrier thread. But you can see that like my execution is actually pretty much the same, because like when I will get to my thread A to the sleep method, I will actually unpin it from that single carrier thread, and I can mount thread B. So each of them is doing their sleep, like not actually blocking any thread. But what will happen if I just put this into synchronize, this doesn't matter, like this. Now, again, I have only one thread. You will see that I basically, for the duration of that A, I couldn't really unmount it from that one carrier thread, and my thread B only started when my thread A finished. So this is that actual issue that if I think, and this is always not working, so but we will try, of course. Yeah. Only 2 terms. You will see that I am still starting with one thread because I have parallelism to 1, but because I allowed that fork join pool to scale to 2, it actually did. So I already created one more thread to handle that second request. Of course, this is something that is not really your issue, because typically you can find synchronized blocks or monitors in your own code, but typically you are calling some library codes like insert into a database or something similar. So it's not really in your power to actually remove all synchronized blocks in your calls. And this can be anywhere in your stack. Actually, let me try this, because I should have this Java source. Yeah, I have here this property trace pin threads to basically full. So we can actually see, let me do this. We can actually see that that virtual thread 1 actually emitted that event that it's pinned, and we can find it really on where it was done, blah, 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 in thread sleep in my virtual method directly on a line where it basically I pin it. This actually is really easy to like mitigate, and I will, for the demonstration purposes, move this into a separate method because it's easier to work with. Yeah, that's no. That B is not. Oh, let's do it like this. So, of course, if I put synchronize here, it's exactly the same thing. So I will get exactly the same issue. Basically, how you can mitigate is remove synchronize and replace it with private static reentrant lock. So reentrant lock is actually able to not emit this event. This is why they are working to actually introduce the same concept inside the synchronized block inside JDK. And basically, in my method, I can just do lock, lock, and typically in finally block, you want to do lock, unlock, and this is functionally exactly the same, but this time I will not get that pinning event. And you can actually also see it on the timestamp, so you are seeing that both thread A and thread B are starting actually almost at the same time, even if they are running on the same carrier thread. Okay, let me put this back to this method, because like we don't need to have it extracted, if it was just easier to demonstrate. So we are back in my like original example where we just did run on one thread. Maybe I will also mention that we actually did a little bit of work on top. Where are my tests? And we actually, at least in Quarkus, you can annotate your test with this virtual thread unit, and then you have annotation should not pin, which will actually listen for these events. And if you pin, we will basically fail your test. I don't know, like, we have some time, I can show you. So in my virtual dev mode, I can just press R to run tests, which is called continuous testing. So you here will see that I'm running. I can close this. I didn't want to close it. I will show you later. So you see that all my 2 tests are passing, and these tests are calling this problem virtual resource, which is a new resource, which is here, which I can basically, not reactive, but virtual, I can very easily pin, which is doing exactly the same thing. So you can see that this doesn't really matter like on what you are doing for that blocking operation, it just cannot happen. And if I now rerun my tests, which are already rerunning, because if I just save the file, Quarkus already detects that I made changes and it will rerun my tests. you will see that somewhere here I was expected not to pin, and my carrier thread was pinned. So it's just nice to have this kind of functionality, because then you can see it right away that you are calling something which you should not. OK, so when this is passing, we can open a new terminal again, because I forgot to show you what happened with that actual carrier threads, because that fork join pool can actually scale both ways. So if you are not creating new virtual threads, that carrier threads will be actually deleted, and they will be recreated again when you have need. OK, going back to IDE, or maybe going back to slides. This would be more or less everything on pinning, because this is just going to happen, or it's not. Like, you need to be aware that these kind of situations can happen. The second issue is monopolization, and this is actually something which either JDK or framework cannot do anything about, because if you just execute any computation that is basically utilizing that virtual thread, you will basically utilize the carrier thread. And there is, if there is nothing which is basically doing blocking I/O, so sleep or HTTP or whatever file writing, basically you will never be interrupted. You will never be unmounted from that carrier thread, and you are exactly in the same situation. You are just blocking the carrier thread in a different way. And you are getting into exactly the same problem, because again, if you run out of carrier threads, JDK will create new carrier threads. So yeah, so you need that I/O operation, because otherwise you cannot really move out of that state. And we can really easily demonstrate that. Where is my virtual method? If I will just replace this sleep with while, very hard work, and I'm still limiting my fork join pool to only one carrier thread, you will see that I will just execute thread A start, and now I'm continuously busy on that one carrier thread, so I will never actually yield it for thread B to start. But all I need to do here is, all I need to do here is only, and I will do it like this, sleep for 1 millisecond, and this is enough to actually create that unpin event, so it actually will be available for 1 millisecond for that thread B to start. And after thread B starts, it will also unpin it, basically, for the duration. And this will, again, just wait for 100 milliseconds. And after 100 milliseconds, I will get, again, one window, basically, to execute the thread B end. Because always there is somebody that will ask this, yes, there is a yield method on thread class. So you can do actually the same thing like this. I will close this, and it will do the same thing. Just if you read the Java doc of this yield method, you will find out that it's actually not recommended to be used in production. So don't use it in production. OK. So as I mentioned, basically, there is nothing we can do about this. I will put this back. So if you are doing any long computations, just don't do them on virtual threads. The next big problem that we have is that basically thread local objects and object sharing. If we again rewind back to that original processing with I have small number of threads, typically in a pool which I am reusing on purpose, we typically really wanted to reuse as much as possible. So we actually, on purpose, at least in frameworks, are creating expensive objects which take long time to create, and we will put them into thread locals, so they are actually reused with every execution. And you can imagine like JSON deserialization or object mapping, etc., or transaction IDs. This is also something which is very heavily propagated to thread locals. This was, of course, something which, if we know that we have like a fixed small number of threads, this is OK, because we are executing that bigger chunks of work only once for each thread. But thread locals, actually, from later release, they have been not supported since the beginning in Project Loom, but they added support so you can use thread locals everywhere in your virtual threads. But how they are doing that is basically they will copy the value of the thread local for each virtual thread. So you see that if we had these like really big and expensive objects, now we are creating it for every virtual thread, billion times. So yeah, I can also show you this because this is not so hard to demonstrate. So if I just create a virtual thread here, oh, thread local, let's do private thread local, thread local, thread local with initial. Let's do just UID, random UID. And in my virtual threads, I will just print it as a first thing. So thread local, thread, come on, thread local get, and copy paste this. So if I now run my application, I should be correctly getting, where is it? Let's make this a little bit bigger. 2 different thread locals created because like my virtual threads are actually different threads, which is correct. But if you realize that they are actually running on the same carrier thread, on the same platform thread, you see that this is kind of magic, and that magic is done by copying. So if I just change my, let me copy paste this, my virtual thread, oops, not this one, my virtual thread executor and replace it with new single thread per executor without factory. So now I'm still having only one thread, but this time normal platform thread. You will see that I am getting the same object because I am running on the same thread. So this is, you see what kind of issues we are dealing with. Again, probably not something that you will run into in your own code, but when we are basically doing this on a server side, then we need to adjust our code. And of course, if you are doing any complicated work in your constructor, this will have direct effect because you are creating basically these or copies of your expensive objects when you are creating virtual threads, which is only happening when you will get requests. So, oops, where we are. So that would be more or less thread locals. And last thing is basically you need to realize that you, from your perspective, you are still writing blocking code, but this code is no longer executing solely on one thread. So you need to count and use thread-safe variants of methods because you are now actually going to be interleaved with other threads. So if you are going to do something in objects which are actually keeping some state, then you should be aware and use thread-safe variants. So this would be more or less the issues that we see with virtual threads. So after this, who thinks that Project Loom is still future of Java? I always get more hands. This is interesting. I also think that we will basically all move to virtual threads one day, but not yet. Basically, the issue is that we, as a Java ecosystem and mostly frameworks, need to adjust to virtual threads. We need to rewrite, and we are already rewriting Hibernate, Jackson, and libraries like this. So it will take some time until we will basically catch all the potential issues, because you need to realize that all of these problems that I showed you in this talk will only happen when you will have big loads on Black Fridays. And you will run into these kind of issues probably without real failures if you are not going to play with that max pool size, because you will be limited to 256 threads, but that's not that much. Of course, I already talked about JDK 23 probably fixing the synchronized block, so that will be that would be enormous help, but native libraries are still an issue. And this is probably not something that we can get around that fast. And thread locals, there is a new experimental APIs code values. I think that there have been several talks at this conference, so I don't really want to dive into it, but there is also a way how to rewrite it. So just to sum up, I really think that we will get there, but it will take time. Eventually, Quarkus will also move full to virtual threads. But with the current state of the ecosystem, it's just we don't really want our users to shoot themselves into their legs. And this is why you need to explicitly declare everything that you want to run on virtual thread with that annotation. So if I would be asked myself, like if I see Java really moving to virtual threads, I would say yes, but in time. And with that, that would be everything. from my presentation. So you can see, find slides, and I will push the code that I coded here to the repository, which is there. And you can get 45% discount for my Quarkus in Action book, which is now in early preview and will be released by the end of the year. And yeah, if you have any questions, I can take them now. And I also have some Quarkus stickers if somebody wants to come here after the talk. Thank you.